Solving and graphing absolute value inequalities. An absolute value inequality is an inequality that contains an absolute value expression. Their solutions and graphs are very different from absolute value equations, but the methods to solve and graph them are similar. Let's start with inequalities that center at x equals 0. When solving absolute value inequalities, there is one important step to remember that is different than solving equations. Let's start with the absolute value of x is less than or equal to 2. Recall from equations that the solutions can be found by setting up two inequalities using opposite expressions. So we have x is less than or equal to 2, and the opposite of x, negative x, is less than or equal to 2. Remember that the absolute value of opposites are equal. So far, everything is the same as with absolute value equations. This is where it changes. To isolate the x in the right equation, we need to divide by -1. And recall that when dividing inequalities by negative numbers, the symbol flips. So the two inequalities are now x is less than or equal to 2 and x is greater than or equal to -2. And the shortcut we use is that when you set up the second inequality, the opposite value, flip the symbol. I'll read that sentence again because that's important. The shortcut we use is that when you set up the second inequality to the opposite value, flip the symbol. This leads us to graphing the solution. The other difference between absolute value equations and inequalities is that when graphing their solutions, shading is required. The shading varies completely on whether you are working with less than or greater than inequalities. We'll go over each one separately. Less than inequalities. Consider this inequality that uses the less than or equal to operator, its solution, and its graph. If the inequality is less than, replace the less than or equal to symbol with just the less than symbol. We'll look specifically at the absolute value of x is less than or equal to 2. The solution to this inequality is as follows. X is greater than or equal to -2, and x is less than or equal to +2. Notice that the direction of the inequality is reversed when the solution is negative. The word "and" is significant here. The "and" means that the solutions need to be true for both inequalities. The solution can be written as this. 2 is less than or equal to x, which is less than or equal to 2. Notice the graph of the absolute value of x is less than or equal to 2. Some observations I want to make before I read the paragraph. At both -2 and +2, the circles are closed, meaning those values are included in the solution. Everything that is covered with the red line is also part of the solution. That includes real numbers. Now I'm going to read the paragraph. The absolute value of x was defined earlier as the distance between a number x and the origin, and the distance is always positive. This explains why -2 and +2 are solutions to the equation absolute value of x is equal to 2. The solutions to the absolute value of x is less than or equal to 2 are all numbers x whose distance from the origin is less than or equal to 2. The shaded region above includes all the points that are within 2 units of the origin. And now we will turn our attention to greater than inequalities. Consider this inequality that uses the greater than or equal to operator, its solution, and its graph. If the inequality is greater than, replace greater than or equal to with the greater than symbol. Let's consider the absolute value of x, which is greater than or equal to 2. The solution for this inequality is x is less than or equal to -2, or x is greater than or equal to +2. The direction of the inequality is reversed when the solution is negative. So notice it started out greater than, but for the negative solution, we're using less than. The word "or" is also significant. The word or means that either solution is correct. It is actually impossible for a number to be less than -2 and greater than 2 at the same time. The or statement means one of those two statements has to be true for the entire statement to be true. Examine what happens when the greater than symbol is used. So now we're focusing on just the greater than. If we have the absolute value of x is greater than 3, all numbers in the shade, I said that again, all numbers in the blue shaded regions are the solutions to the inequality. Pick any number in either region to verify this statement. So let's just say we pick -4. The absolute value of -4 is +4, and +4 is greater than 3. If I pick 6, the absolute value of 6 is 6, and 6 is greater than 3. This time, there are two separate regions, and the solution will be written as x is less than -3 or x is greater than +3. Again, use the equation distance idea. The solutions to the absolute value of x greater than 3 are all numbers x whose distance from the origin is greater than 3. There are two distinct shaded regions that satisfy this condition. The set of numbers to the left of -3 and the set of numbers to the right of 3 are greater than 3 units from the origin. The solution to this set of numbers were where x is less than -3 or x is greater than 3. Practice problems set 1. Consider the absolute value of x less than 5. There's three things we're going to ask you to do. For part A, which of the following x values are in the solution set? So you want to consider -7, -2.5, 3.6, 4.9, and 8.75. We got 5 things we want to consider. For part B, you want to sketch a graph of the solution set on a number line. And for part C, you want to rewrite the absolute value of x less than 5 without the absolute value. This is a good opportunity for you to pause the video, and then when you got your answers written down on a piece of paper, resume watching the video to see what the answers are. Now that you've had an opportunity to work on these yourself, let me reveal what the answers are. So for -7, that is not a solution. -2.5 is a solution. 3.6 is a solution. 4 is a solution. But 8.75 is not a solution. Your graph would contain open circles on both -5 and +5, and everything covered with the blue line in between those values would be a solution. And finally, your solution set for the absolute value of x less than 5 without the absolute value would be -5 less than x, which is less than +5. Here's a refresher on how we accomplish that. So what I did was I start with the absolute value of x is less than 5. I have to consider both the positive and negative. So I have x, -5, and over here I'm going to put x and +5. Now here, the less than symbol just translates down for the positive value, but for the negative value, I reverse and I go from less than to greater than. So my two solutions are x is greater than -5 and x is less than 5. And then we can combine these two into one inequality where we can say x is greater than -5 and at the same time less than +5. Here's a second set of practice problems. This time we are looking at the absolute value of x greater than or equal to 2. For part A, you want to find which of the following x values are in the solution set. Part B, you want to sketch a graph of the solution set on a number line. And part C, you want to rewrite the absolute value of x greater than or equal to 2 without the absolute value symbol. This is a good chance for you to pause the video, try these three parts of problem set 2 by yourself on a piece of paper, And when you have your answers, resume watching the video to reveal the answers. I trust that you've had an opportunity to do that. Here are the answers. So, -3 and 2.1 are solutions. The other three values are not. When you sketched a graph of the number line, this is what we call an OR statement. Anything less than 2, less than or equal to -2, going to the left, or anything greater than +2 going to the right. Notice the circles are closed, meaning that -2 and +2 are also part of the solution set. When we rewrite the absolute value of x greater than or equal to 2 without the absolute value symbol, it is going to be x is less than or equal to -2, or x is greater than or equal to +2. And here's how we accomplish that. If I start with the absolute value of x greater than or equal to +2, I have to consider both the positive and the negative. So I have x in -2 and x in +2. Now for the positive, I just bring this symbol right down for the positive case. So x is going to be greater than or equal to +2. But for the negative case, I have to reverse the inequality. So it was greater than, it's now going to be less than. And again, it's impossible for a number to be less than -2 and greater than +2 simultaneously. So we use the OR statement, writing it as two separate inequalities joined by the word OR. Now let's add constants within the absolute value to solve equations or inequalities that look like this. The absolute value of x minus 4 is less than or equal to +3. So we split the inequality into two and solve each. Remember to flip the symbol when setting the inequality to the opposite solution. So we have x minus 4. Notice this switch right here. It was less than. It's going to be greater than or equal to -3. For the positive case, we keep it the same. It's still going to be less than. Solving for x, we get x is greater than or equal to 1 and x is less than or equal to 7. The solutions are all numbers x which are greater than or equal to 1 and less than or equal to 7. This is a graph of the inequality. Notice the closed circles over both 7 and 1, and all the values in between are a solution to this inequality up here. Greater than or equal to inequalities within constants work the same way. The solution for this inequality, the absolute value of x minus 2 is greater than or equal to 3, would break down as the following. X minus 2 is less than or equal to -3, which results in a value of x less than or equal to -1. Notice the direction of the inequality is reversed when the solution is negative. For the positive side, we have x minus 2 is greater than or equal to 3, just bringing this inequality straight down. And the resulting solution would be x is greater than or equal to 5. We get that by adding 2 to both sides. Notice the word OR. The OR statement, the word OR, means that either solution is correct. So for this to be correct, you can pick a number in this region here, or you could skip over and pick a number in this region here. Both of those regions would give you a solution to this inequality. Practice problem number 3. Solve for x and graph the solutions on a number line. Now to solve this problem, I'm going to use a basic math equality that the absolute value of opposites are equal. So if I consider any number like the number 10, the opposite of 10 is -10, and the absolute values are going to be equal. If I have a value x, the opposite of x is -x. The absolute value of opposites are equal. It's the same thing for subtraction problems. If I have x minus 5, the absolute value of x minus 5 is 5 minus x, and the absolute values are going to be equal. You can verify this by picking any number for x and trying this out. You'll see that the absolute values are going to be equal. Now on to the solution for this inequality. As we stated, I can rewrite this as, instead of writing x minus 5 minus x, I could write it as x minus 5. And I have to consider two cases, x minus 5 with negative 3. And in this case, I reverse the inequality. So instead of having less than, I have greater than. And over here, I'm going to have x minus 5. Keeping the inequality to less than, I consider the positive case of positive 3. So here is the simple algebraic steps. And we see that x, after I add 5 to both sides, is going to be greater than 2. And over here we have x is less than 8. So writing it out, it's going to be x is greater than 2 and x is less than 8. What you see is the graph of x greater than 2 and x less than 8. This can actually be combined into one inequality of x is greater than 2 and x less than 8. Practice problem number 4, where we are going to solve for x and graph the solutions on a number line. We're going to consider the absolute value of x minus 2 greater than or equal to 5. Now what's nice here is that x is already positive, so we don't need to rewrite it as an opposite. We can go ahead and consider the two cases. Case number 1, we'll have x minus 2 less than or equal to negative 5 by reversing the inequality for the negative number. And for the positive case, we're going to take x minus 2 is greater than or equal to 5. Adding 2 to both sides, we are going to get two solutions. X is less than or equal to negative 3. And here's the graph of x less than or equal to negative 3. We also get x is greater than or equal to 7. And here's the graph of x greater than or equal to 7. Let's suppose we are given a graph and we want to create an inequality from the graph. That's what we're going to turn our attention to now. So what if a graph is given and you are asked to find the inequality that generates the graph? The top graph is a less than or equal to graph. The bottom one is a greater than or equal to graph. Notice the characteristics of both. By looking at the graph, make a mental note of what determines a less than or equal to graph here and a greater than or equal to graph here. We're going to work with the top one first. First, we will find the center C and the distance from the endpoints to the center. It will be the same for both, just like the equations. So we know that the solutions are x is equal to negative 5 and negative 1. The center C of both of the two endpoints is basically the average. You're going to take negative 5 plus negative 1, which is negative 6, divided by 2, gives you negative 3. You can see the dashed vertical line at x equals negative 3. To determine the distance, what we do is we take the left endpoint and subtract it from the right endpoint. That gives you the total distance. Dividing it by 2 will give you the distance from the endpoints to the middle. So what you see here is d is equal to negative 1, the right endpoint, minus negative 5, the left endpoint, divided by 2 gives you a distance of 2. Next, we fit the values of c and d into the general equation. Right here, the absolute value of x minus c is less than or equal to d. So we know that c is negative 3. We know that d is positive 2. Now x minus negative 3 is the same thing as x plus 3. So our final inequality is going to be the absolute value of x plus 3 is less than or equal to 2. And now we will do the same thing for the second graph. Now, the way the arrows are pointing indicate that this is a greater than or equal to graph. The solutions are negative 5 and negative 1. The center C of the two endpoints is found by taking the average of the two endpoints, negative 5 plus negative 1, divided by 2 is equal to negative 3. So the dashed vertical line at x equals negative 3 indicates where the center is. Now to find the distance, what I do is I take my left endpoint, negative 5, and subtract it from my right endpoint, negative 1. So d is equal to negative 1 minus negative 5, which is positive 4. Positive 4 divided by 2 is 2. So the distance from the endpoints to the center is 2. Next, we fit the values of c and d into our general equation. The absolute value of x minus c is greater than or equal to d. We know that c is equal to negative 3, d is equal to 2. So x minus negative 3 becomes x plus 3 is greater than or equal to positive 2. Inequalities, practice number 5. What absolute value inequality would give the graph of the solution as shown below? Take a look at this solution shown here and see if you can calculate the or come up with the absolute value inequality that represents this solution. This is a good opportunity for you to pause the video. When you have your answer, resume watching the video and compare your results. And welcome back. So this graph results from the greater than absolute value inequality. We know that because we have what I call an or situation. We have x is greater than negative 1 or x can be less than negative 8. The two solutions cannot occur simultaneously, so you have to have one or the other. Since this graph results in a greater than absolute value inequality, and we've determined that the endpoints are negative 8 and negative 1, we're going to calculate the center. So the center C is going to be, of these two solutions, is going to come like this. I take negative 1 plus negative 8 and divide that by 2, and the center is going to be negative 4.5. I essentially am finding the average. So we're going to draw a vertical line at x equals negative 4.5. There's negative 4.5 right there. Now to calculate the distance, I take the larger number and subtract off the smaller number and divide by 2. So the larger number is negative 1, the smaller number is negative 8. Negative 1 minus negative 8 divided by 2 is going to be 3.5. So now I make my substitutions. The center is going to be negative 4.5. That goes in for C right here. The distance is 3.5. That replaces the variable d. And the only thing left for me to do is to combine the fact I'm subtracting a negative. Subtracting the negative is the same as adding. So my final result is going to be the absolute value of x plus 4.5 is greater than 3.5.